And welcome back. In this video, we're making our own exchange-traded fund of a NASDAQ index. And yeah, before we do that, I hope you all know what an ETF or exchange-traded fund is. So basically, today we have many different indices, for instance, on stock markets. And what an index like the DAX or the S&P or the Dow Jones typically does, it aggregates the development of a certain amount of companies, and the aggregation is done for different indices in different ways. Okay, but basically what it tries to reflect is the systematic development for a certain group of companies. And this is another way how we can picture what a reduced dimension does here, okay? Because in the first autoencoder video, I told you that sometimes we use the reduced dimensionality representation of original feature data to, for instance, generate prediction models then. And we do this because we have fear for the curse of dimensionality. But also, especially in economics, systematic behavior is something really important. Because systematic behavior of stock markets or of the credit market or something, that is especially when we think about real the crisis in 2007, 2008, 2009, or the dot-com crisis or the Eurobond crisis. This is where the market systematically, for instance, experience a worse development or a bad development, and this is something which can be very interesting for us to learn about, and this is something which is typically more important than the development of single stocks, for instance. Okay, when we have an ETF, that is because we can not directly invest our money into an index. An index simply reflects the development for a certain group of companies, but if we want to have the value of that is represented by the index, if we want to do this on our own, we would need to buy all the stocks that are in the index with a certain weighting that is sometimes even hard to find. And and also it would cost, typically if we do this as a private person, a lot of transaction costs, because you would need to buy many different single stocks. Especially think about the S&P 500. That means you as a private person would need to buy 500 stocks with certain weightings. Kind of a bad thing to do. And that is why big institutions or funds collect money from different people and do this professionally, and with their knowledge, and also with the bigger funding they have provided by private people and also, of course, by other institutions, then they can invest in all these stocks. And what they typically do, or when we are investing in an ETF, we are doing what's called a passive investment strategy. That means they do not try to develop any algorithms which predict and outperform the market. They only try to replicate the development of the index, and that means they kind of need to track with which weight each of the stock is kept in the index at the moment, and all these weights typically change over time as the value of the single stocks change over time. So with that in mind, they just try to have as much money invested as it is resembled by the weight that is currently used in order to calculate the value of the index. Okay, sounds complex, but if we have 10 companies or 30 companies, and for some indices it's more like a value weighting, means stocks that are more valuable are weighted with a higher weighting, and this higher weighting or these weightings are then aggregated when aggregating the overall value of the index. But index calculation sometimes can be messy and can be a little hard to understand, not because it is so complex, but sometimes the documentation isn't even public, I think. Okay, so now assume for the moment we also want to have a similar development as an index. We know which companies are in the index, but we are not aware of the weightings. And another way to derive weightings is simply to build a model which, condenses the information of all the development of the single stocks into a single number, and then use the weightings that we need here in order to generate the single number as an indication which of the stocks is more exposed to the systematic behavior. So which of the stocks is more exposed when we use when we want to calculate the single number. So which of the stocks has the highest weightings here in absolute terms. And then using this information, we will use also this weight to generate a portfolio of those stocks and hopefully have a similar development as the original index. Okay, this sounds really complex, but as before, let's go through the code here. And let me just quickly already start here because it takes a few minutes when we download the data here. So what we're going to do here, we use the NASDAQ, and for the NASDAQ I think there are 3 or 4 indices available, but this will be the NASDAQ 100, having typically 100 tech stocks, and these are like the first 5 you can see here. Okay, so we can see there's Alphabet, so Google, Activision, especially known to people who like to play certain computer games. We have Adobe, and so on and so on. But we have 100 companies here, and the NASDAQ will be the index who represent the systematic behavior or the systematic value development of those 100 companies. What we can observe is the development of those 100 companies, and also later we can observe the development of the index. But what we're trying to do here, because let's for the first moment, let us simply ignore the fact that those are the 100 companies of the NASDAQ. And now just think about it in a different way. Okay, we have 100 companies. Each company has currently or in the past 10 years a certain development on the stock market. So what we usually do here, so by the way, I'm downloading the data here for all the stocks with a professional API of financial modeling prep, and I leave this public to you because I have here the company version. So we have a large limit that can be used and downloaded by us each day. So if you want to use this in the course to play around with it, be welcome to do so. Please not do this too extensively, because then we hit the limits and then I need to delete this API key and generate a new one. Okay, but as long as every participant in the course is using this responsibly, or anyone seeing this video, there should be no problem. So what we have here, we download the stock market data for each stock. So that is how it looks like. So we have way more data at the moment than we need. So in this data set, between like the past 10 years for each stock, so here we have the ticker, we have the typical things: open, high, low closing prices, the adjusted closing price, the volume, and so on and so on. So what I do here in the first step is to simply use only the adjusted closing prices of each company and sorts the data set by its date index. So it starts in 2010, and now in each column we have the development of the stocks. We can see here that there are nowadays a few stocks that do not have a history that is that long as I wanted, and that is why I we can see also this here when taking at the missing values. So there are a few companies which do not have a history as long as I wanted. So that is, in the first step, I exclude those companies here. So here by the drop NA method, and axis 1 means column wise, and this leaves us now with about 79 companies with the full history of the data I'm looking right now, which is, I defined in the beginning here, between 2010 and 2021. Okay, now stock data or the closing prices themselves are usually non-stationary and also on very different numerical scales. Both is disadvantage for the modeling we're going to do. So that is why also I now calculate the log returns of the stock prices for each company. Also, log returns is something where we are the most interested in, at least on individual stocks or for the whole portfolio, because that is how they are additive when it comes to deriving the portfolio value over time. And then this is our original data. So we use this data. So for each column here represents the development given by the log the log return of each day over approximately 10 years. Okay, and now what I'm doing here in the first step, I show you that there is a rather high correlation, or at least is only positive correlation among all log returns from the stocks. So the more light the color here is, the higher is the dependence. I prefer to use Spearman correlation because it is a rank correlation and typically not as prone to certain shortcomings by Pearson correlation, which is only able to detect linear relationships. But the only thing that you should realize here that, of course, there is, as always for stock market data, a comparably high correlation among all the assets. And having a high correlation among all the variables here means it is likely possible to have a few less variables, but still, have the majority of the information given in the development of all the companies that is given here. And that is, assume perfect dependence between two variables, then it's always would be enough to know one value of the one variable. And in a similar way, it kind of is how you could picture it here. If we have high correlations among all the original feature variables, then it's way more likely for us to succeed in a good regeneration of the original data when using a lower dimensional representation. And furthermore, this we are not aiming for a perfect regeneration here in the moment. What we are going to do now is we directly try to do this how I would start at least doing this if I really want to do this in practice. So we start in 2010. So here I call this start ETF, but that's kind of misleading here because that is in 2012. Okay, what I mean with start ETF is where I really would not the data where the data starts, which I want to use for estimation. This is where I want to present my ETF to the public, such that people can give me money. I derive the weights we need for each company and how much of each company we need to buy in order to have a similar development as the original index here. So I always look back for 2 years here. That is by the relative delta function here. So our estimation starts, as the name start suggests, in 2010 in the beginning. And then it ends with the starting date. So est_end is the same as the starting date. So we use the data between 2010 and 2012 now in order to estimate our first autoencoder. And let's just do this for a single time. I do this in a loop here later. But as always, when you have a loop here, and if you're not sure what is done here, just do this as I'm doing it now, okay? So we have our starting dates, we have where the estimation should start, we have where the estimation data ends. Then I am taking the log returns, so in the original data set, they're going from 2010 until 2021. Now I call the training data, or I define the training data object here, and now it's just the data between 2010 and 2012, okay? Then if we want to use as we always, for neural networks, we are going to use standardized data, so that is why I'm proceeding, or why I'm using the standard scaler here and bring the original data now to the standardized version, which then looks like this here, okay? Now, what is going to be used later here, let me just take a look. What we definitely are going to need is to import TensorFlow. So what we are now going to do in the code later, but we will do this again and again and again, is we're going to define a simple autoencoder, as you can see here. But this is nothing new. The only thing I'm doing here is dynamically take the shape of the original data. This is simply the amount of features, the amount of variables, in our example, the amount of companies that we have here. And this is not necessary, but I also I set the bias to say the model not to use a bias. I will show you in a few minutes why I'm doing this. But this is nothing new here, okay? So this should be already known from your from the previous video, okay? Now for a given data, we will then always compile and fit the model. So let's do this also here. You can define always the network outside of a loop, but you need to do the compiling inside of a loop if you want to refit the neural network again and again, because by calling the compile method, again, the parameters of the model are newly randomly initialized, so the model starts at 0, so to say. So fingers crossed, let's hope this works now. And now we are, yeah, I said this it's a very short learning time of 25 epochs, and I set verbose to 0 not to have this output here, but that is what's happening. But if I set verbose to 0, then we're not seeing this. And now the autoencoder for the first, using the data of the first 2 years is estimated, okay? Now let's take a look at the encoder weights, and I will quickly tell you why. So again, let's use flatten here. Sorry. Okay. So we have 80 companies here, and we have 80 weights here. So when we use with our encoder, so again, if our data here, I hope this works. Well, we don't need this, the encoder predict with our train data brings us our 80-dimensional samples to 1-dimensional samples. Okay, so sorry. So if we take a look at the training data and its first sample, then we have 80 values here, and this is the standardized version of the log return of the first company at the first point in time. This is the standardized version of the log return of the second company at the first point in time, and so on and so on. So we have 80 values here, each value representing the log return at the first point in time in our data sample. After the transformation of the encoder, all these 80 values are condensed to a single value, which represents the systematic behavior of those 80 log returns. Okay, that's like the idea here. And now we dive into another logic. So each of those, in order to make this single value here, we weight each of those values here with a weighting and then just aggregate it. So sum it up. That's what's done mathematically here. And those are the weightings. They are estimated, and they are estimated as we learned it from before, how it's done for autoencoders. And as you can see here, do not look at the sign, but obviously some of those weightings are higher than others. So here we have, 0.1. Do not look at the sign. And here we have a very small weighting, for instance. And here we have something in between. The higher the weighting, the more exposed the original value is to the lower dimensional representation. More exposed means it's, more dependent to the reduced dimension. And if we interpreting the reduced dimension as the systematic behavior of all the companies, which is also the index typically, then a higher weight here corresponds with a larger dependence on the systematic behavior. And that means we need to buy more of the companies that have a higher weighting here in order to, or let's say like this, the higher the weighting here, the more we buy of that company in order to have a similar progression as the systematic behavior of the companies has. As I said in the last video, in the beginning, this is really intuitive and it's already hard to explain for me to you, so I guess it's even more harder for you to understand. But what I try to bring this down one more time, and I try to explain it as intuitive as possible in a moment. If we have many companies, and if we bring the development of those companies into one single number, which is kind of an aggregate and corresponds to like the systematic, one could say average development of those companies, then the companies which have the highest dependence on those systematic development, these are the companies which we would need to hold the most in our portfolio in order to copy a portfolio which behaves as close as possible to the systematic development. And the index is here what is the systematic development of the companies over time. Okay, and that is why now we are going to rescale those weights such that we could use them when we build a portfolio of all those companies, with the idea that the companies which are more exposed to the systematic behavior are also the companies that we want to hold the most, in order to have a portfolio which behaves as close as possible to the systematic the systematic behavior of the companies. Okay, so as we will have a long only investment, we only buy companies here and not sell any companies or short sell. First of all, we use the absolute value of those weights here. So again, in absolute terms here, the higher the value is, the more exposed the single company to the systematic behavior. And now we need to normalize those values such that they are between 0 and 1 and they sum up to 1. And that is simply done by using the sum of those absolute weights here. So if we do this, then we have values here which are all between 0 and 1. And if we sum all these values, or we sum over all these values, it should sum up to 1. So it's close to 1 because of rounding errors here. And these are the weights that we now are going to use. So we use the data of January 2010 until January 2012. And we use the data in order to estimate a model, which helps us by determining weights, how much of each company we are supposed to buy. And now we use these weights and buy each stock with a weighting that corresponds to this value here. And these weights are then held, in this example, I assume for a month. And then we hold each of the companies with these weightings for a month. And a month later, we again will use the past 2 years in order to estimate an autoencoder, in order to derive the weights with this logic given here. and we rebalance the portfolio. And we'll do this month by month by month, and that is why we have here a loop until we reach the end date, which is 2021 in September, I think here in the example. And the only thing I'm doing here as a simplification is I am assuming that I could buy stocks as they are given by the weighting. So I don't know, assume we have 1,000 euros and I'm supposed to invest 25% into of that into a company, then I have 250 euros to spend for the stock of the company. The problem in reality would be that I can only buy complete single stocks. So if the stock is, I don't know, worth 248 euros, then I can buy one stock, but 2 euros remain. So I'm not really buying 25%. I would buy 24.8%. So in practice, that kind of is a problem, which could also worsen our replication. But here, for the moment, I'm assuming that I really can invest 250 euros in the stock. And what I do here, you can find it out if you check this example out in more detail. I weight now not the log returns, but the closing prices in order to estimate a portfolio weight at a certain time. And that's just because of the, log returns are non-additive in a cross-section. They are additive over time. And discrete returns are additive for the cross-section, but not over time. That's a problem, and that's why I'm directly using the weights and multiply them with the closing prices, not the log returns, because this will give us a weighted development of the original stock prices. And with those values, then later I can determine the log return of my portfolio. A little bit complex when explained in that way. But for the moment, I would say most important for you to understand here or to develop an understanding is that what I'm doing here. And what I'm doing here is I condense the information of 80 companies into a single number. And to do so, I need to weight each of those 80 companies with a certain weighting. And when we derive the weightings with the autoencoder structure, what is made sure is that the single number in between keeps as much as information as possible, or the most relevant information of all those 80 companies. So one could also say it keeps the systematic behavior of those 80 companies. And if I want to have a portfolio which has a development similar to the systematic behavior of those 80 companies, which is the index in the end, then I buy more of companies which are more exposed to this single number, so to the reduced dimension, to the systematic development. And that is why I use the absolute values of the weights of the autoencoder here. So as I said before, I think this is kind of non-intuitive and difficult to understand. But if you understand this, I would say you really have a good impression. Let me just, before I explain this, you have a good idea what is meant by systematic behavior of certain values over time and so on. So let me just quickly click play here. So this is now done month by month. So at each point in time, I'm using the past 2 years in order to derive the weights. And then with those weights, I use the weights to invest for a month. And then after 1 month, I would, take a look, fit a new model using new data, try to find out if I need to change the weightings in my portfolio. If I have so, I would do so. And I will do this month by month, and then we take a look in a few seconds how this looks like and how this succeeds in having a portfolio which behaves similar to the systematic behavior of all those 80 stocks. And then in the end, we compare the systematic behavior and the value of the portfolio and compare it to the index that we originally trying to regenerate here, okay? But what we have here now, we need to wait until this reaches 2021. And I'm going to delete a few of those here. So that was, and that is, and that can be deleted. And guess that we almost finished. Almost. So I mean, I'm not 100% sure, and of course also this could be extended in using stacked autoencoders and so on. But then we could, it really gets. This is just the beginning. We would need to alter and change certain things, and it gets more complex. But it would also provides us new possibilities. But for the moment, let's just keep it as simple as it can be, at least when it comes to the idea or the definition of the autoencoder. Because yeah, I think it's already complex enough at the moment. Here I also use the API. I checked which of the indices, as there are many indices available, and now I try to find out which indices are given for the Nasdaq, and now I compare here the my ETF with the Nasdaq 100, but we could also compare it with the other Nasdaq indices that are given here. You simply can do this by yourself, and you can do this when you insert the one of the other symbols given here. Okay, but here I download simply the data of the Nasdaq, such that we can compare it. And now what I do here is to compare the portfolio value of my portfolio, which I generated in the way I described now in the video. And you can already see that it's kind of magical, I would say, that it almost looks similar, speaking about the development of the portfolio value and the development of the index. The only thing obviously is different is the numerical range here. And also the behavior of the log returns are also kind of identical. And now we could compare with respect to the log returns also my portfolio, or from my ETF, the standard deviation, it is almost identical. The mean is a little higher, so meaning we perform a little better. The highest loss is even less than for the index, and but also the highest win on a daily basis is a little bit lower. And now assume we would have invested 1,000 euros in the beginning in 2012 in my portfolio or in the Nasdaq. That is how it would look like. So this kind of sometimes it's also a little bit prone to the modeling and to the random numbers that are generated when estimating the model. But usually my ETF succeeds here in performing a little better. And in the end, what also would be important for an ETF is to have a high correlation with the original index. I mean, professional ETFs usually have here correlation almost at 1, but we have also a very high correlation. And now finally, okay, so this already looks also, this all looks very promising to me. It kind of works. We have investments that are and we have a portfolio that is very similar to an index that we want to rebuild, and also it has high correlation. The critical person of you watching this video, or hopefully there are still some people watching this video, may say that we have two shortcomings here. First of all, the simplified assumption that we can buy stocks in weightings as we want to. This is something that we would need to handle in reality. And also, obviously, that is not important when it comes to the comparison here, because we cannot invest in the Nasdaq. But obviously, the success here is a little bit too optimistic here, because also we would have transaction cost, especially if we need to reshift or if we need to change the weights of the portfolio month by month by a large extent. So that is why I'm also visualizing here the development of the weights for each company over time. But I think this also looks kind of very promising. But because as you can see, that most of the weights, they stay at a very similar level over all the time, and obviously, yeah, one could develop certain rules here that we do not really always re-weight, that we do not have to change the weight if it is not significantly different from one month to the other. So for instance, here I would say we would have hold all the same amount of this company all the time. And for instance, for this company, we only would have switched the weight here or changed the weight here, but then would have hold maybe the weight of like this over the whole time in order to, have less transaction costs, which is obviously an important driver for the success in reality of our ETF portfolio. Okay, so this is a practical application how we could use autoencoders. To be honest, if we would if we would stick to this simple autoencoder model, meaning the linear autoencoder with a single dimension, then I would not use an autoencoder. I would use a principal component analysis, because that's numerically more stable, especially when it comes to deriving the weights. But I would say we could do a lot more here. For instance, we could use a stacked autoencoder, then find out we could use more lower dimensions, and we could find out which of the companies are most exposed to which dimension, and then we could use sub-portfolios which are more or less exposed to the systematic behavior. The more exposed ones are more similar to a typical ETF. The less exposed ones could be, for instance, portfolios which share a similar development as the original index, but may be less prone to the systematic development, especially during bad times. So many things could be done here, but for the moment, this is already a rather long example for a real application, how we can use an autoencoder. And I think the most important part in this video here is to understand that an autoencoder can also be interpreted, especially in the financial context, as deriving a systematic development over time, for instance, for a certain number of stocks. Okay, so with that in mind, let's finalize and finish this video, and in the next video I will be way more shorter and simply explain you the idea of general advisory networks. So be excited about it, and see you in the next video. Bye bye.